Right now, inside a high-security aerospace laboratory in Wuhan, China, engineers are firing up a jet engine that should not exist according to basic physics. There is no smell of burning kerosene. There are no heavy supply trucks rolling in with aviation fuel. There is no massive exhaust cloud of carbon monoxide. Instead, technicians pour ordinary water into a pressurized chamber. A high-power microwave generator hums to life. Seconds later, a blinding, blue-white plasma plume shoots out of the quartz nozzle with a deafening roar. It generates immediate, measurable thrust, enough force to lift heavy machinery off the ground. It looks like magic. It sounds like science fiction, but it is real, documented engineering, and it creates an absolute paradox that is forcing aerospace engineers in Seattle, London, and Tokyo to drop everything and take notes. To understand why this is causing total panic in the aviation world, you have to remember one fundamental rule of high school chemistry. Water does not burn. Water is what you use to put fires out. If you throw water into a standard jet engine, you flame out the combustor and bring a multi-million-dollar aircraft crashing out of the sky. Yet, Chinese researchers at the Institute of Technological Sciences at Wuhan University have built a working prototype that converts liquid water directly into an ultra-high-temperature propulsive jet. They are not using water as a coolant, they are using it as the primary propulsive mass. The early performance metrics coming out of these tests are staggering. The experimental water plasma thruster demonstrated a propulsive efficiency that rivals traditional jet engines, generating torque and pressure equivalent to modern commercial turbofans, but without using a single drop of refined fossil fuel. For an industry that consumes over 95 billion gallons of jet fuel every single year, this changes the entire equation. If you are an American traveler, this is not some distant academic exercise. Right now, nearly 30% of the price of every single airline ticket you buy goes straight to paying for refined jet fuel. When oil prices spike, ticket prices skyrocket. When supply chains freeze, flights get canceled. For 40 years, the global aviation industry accepted jet fuel as an unchangeable fact of life. You simply could not fly a 300-ton steel tube across the Atlantic Ocean without burning tens of thousands of gallons of kerosene. China just proved that assumption dead wrong. But how do you actually turn water into a force capable of pushing a commercial airliner through the air? The answer lies in a state of matter that most people have never seen in real life. To grasp why China's water engine project is sending shockwaves through the global economy, you have to look at the massive, invisible trap holding the aviation industry hostage today. Right now, commercial flight is built on a single, fragile foundation: refined jet fuel, known as Jet A1. Every single day, over 100,000 commercial flights take off globally. Together, they burn roughly 200 million gallons of kerosene before the sun goes down. This creates an enormous financial headache for American airlines like Delta, United, and American Airlines. Fuel is typically their single largest volatile expense, eating up anywhere from 20 to 35% of an airline's entire operating budget. When conflict breaks out in the Middle East or refinery pipelines freeze in Texas, jet fuel prices spike instantly. Airlines have no choice but to pass those sudden costs directly to you. That is why a cross-country ticket from New York to Los Angeles can jump from $300 to $800 virtually overnight. For years, Silicon Valley tech leaders and climate activists gave a simple answer: just go electric. We saw electric cars transform Detroit. We saw giant lithium batteries power everything from smartphones to city buses. So, why not just build an electric Boeing 737? Because air travel operates under brutal laws of physics that do not care about green marketing. It comes down to a metric called gravimetric energy density: how much raw energy a fuel holds per pound of weight. Standard Jet A1 fuel holds roughly 12,000 watt-hours of energy per kilogram. The absolute best, most cutting-edge lithium-ion battery on the market today holds around 300 watt-hours per kilogram. Do the quick math. Jet fuel is 40 times more energy dense than our best batteries. If you tried to power a commercial passenger jet with modern batteries, the battery pack alone would weigh more than the entire airplane, leaving zero room for passengers, luggage, or cargo. The plane would literally be too heavy to lift itself off the runway. Electric planes work fine for two-seater flight training toys, but for global transport, battery power is a complete dead end. This reality left the Western aerospace industry trapped. Boeing and Airbus spent billions trying to tweak turbine blades, optimize flight paths, and experiment with biofuels made from cooking oil or corn. But those were tiny, incremental band-aids. They were squeezing 2 or 3% more efficiency out of an underlying design that hasn't fundamentally changed since the 1950s. Aviation was completely stuck in a $200 billion kerosene trap. And then, researchers in Wuhan decided to stop trying to burn things altogether. To understand how a water-plasmatron engine actually works, you have to throw out everything you know about standard combustion. In a normal jet engine, you spray liquid fuel into compressed air, light a spark, and let the chemical fire expand out the back. That chemical fire generates hot gas, which pushes the plane forward. Water cannot do that because its chemical bonds are already entirely stable. Hydrogen and oxygen have already reacted. Water is essentially the ashes of a hydrogen fire. You cannot burn ashes. So, how do Chinese scientists extract massive propulsive thrust from a fluid that refuses to burn? They stop trying to burn it chemically and start ripping it apart electrically. The engine relies on a state of matter beyond solid, liquid, and gas, plasma. Inside the engine's core ignition chamber, water is continuously injected and converted into a fine, pressurized mist. The system then hits that vapor with an intense, localized microwave electromagnetic field, operating at extreme frequencies. When you blast water vapor with high-power microwaves inside a tightly tuned resonant cavity, something violent happens to the molecules. The microwave energy strips electrons directly off the hydrogen and oxygen atoms. This process is called ionization. In a fraction of a millisecond, the water mist stops behaving like liquid or steam. It collapses into a swirling, superheated soup of free-floating ions and electrons, a thermal plasma. The temperature inside this ionized cloud climbs rapidly to thousands of degrees Celsius. At these extreme thermal levels, the plasma expands explosively. Because the engine casing is designed as a convergent-divergent nozzle, similar to the exhaust funnel on a space rocket, the expanding plasma has only one direction to go. It surges out of the back at hypersonic speeds. That high-velocity plasma stream creates tremendous physical momentum. According to Newton's third law of motion, for every action, there is an equal and opposite reaction. The massive kinetic energy of the accelerating plasma escaping through the nozzle pushes the entire engine forward. You are not getting energy from burning water. You are using microwave energy to transform cheap, abundant water into a high-density expanding fluid medium that generates physical thrust. The Wuhan team measured the thrust density of this water plasma system and found that at equivalent power inputs, the pressure generated inside the nozzle matched the internal pressure of modern jet engines. They had effectively produced commercial-grade thrust using nothing more than electricity and tap water. It sounds like a clean, flawless miracle. But bringing this tech out of a small university lab and strapping it onto an actual aircraft exposed a massive engineering obstacle that almost broke the entire project. The journey from a theoretical physics paper to a working thruster inside a Chinese research lab was filled with brutal engineering failures. The team led by Professor Jiao at Wuhan University's Institute of Technological Sciences wasn't the first to think of microwave plasma. Scientists in Western universities had played with ionized gas propulsion for decades, but everyone kept running into two massive brick walls that made the tech useless for real flight: arc instability and nozzle erosion. First, plasma is notoriously hard to control. In early tests, the moment high-power microwaves hit the water vapor, The plasma didn't form a steady, controllable jet. Instead, it behaved like wild, chaotic lightning. It arc-drifted, jumped around, and instantly melted the inner walls of the testing apparatus. Standard steel or titanium engine nozzles dissolved in seconds under the intense thermal barrage of ionized gas. Second, if the plasma flame flickered for even a microsecond, the microwave cavity lost resonance, the thrust instantly collapsed, and the engine flamed out. For an aircraft flying at 30,000 feet, a plasma blowout means immediate catastrophic loss of control. The Wuhan team solved these double nightmares using a series of clever engineering workarounds. To stop the plasma from destroying the engine, they didn't rely on heat-resistant metal. Instead, they built the core ionization tube out of custom-grown, high-purity quartz glass, surrounded by a magnetic stabilization field. By applying a precisely shaped magnetic field around the quartz chamber, they created a magnetic cushion. This cushion forced the superheated plasma into a tight, vortex-like stream down the absolute center of the pipe, keeping the plasma from ever physically touching the solid walls. The engine wasn't containing the plasma with metal, it was containing it with physics. To fix the arc instability, the researchers developed a high-frequency digital control circuit that adjusts the microwave frequency thousands of times per second in real time. If the water vapor density changes slightly, the control system shifts the microwave wavelength instantly, keeping the plasma stream totally stable, smooth, and uniform. When they hooked their modified quartz thruster to a benchtop testing rig, the results blew away expectations. The small prototype produced a thrust-to-power ratio of 28 newtons per kilowatt. To put that in simple language, it proved that a scaled-up version of this engine could generate enough physical force to lift heavy loads, using air and water as its only propellant. The Chinese media immediately ran wild with the news, claiming jet fuel was officially obsolete and that water-powered commercial flights were right around the corner. But as the viral headlines spread across the globe, aerospace experts who carefully audited the research data noticed a massive, unspoken catch hiding inside the numbers. Here is where we need to stop the internet hype train and look at the hard, cold physics, because the viral headlines on social media are lying to you. Water is not the fuel. Water is the propellant. That distinction sounds small, but it changes the entire story. In a traditional jet engine, the kerosene is both the mass coming out of the exhaust and the energy source itself. When you burn fuel, you are releasing energy stored inside chemical bonds. With a water plasma engine, water brings zero chemical energy to the table. The energy required to rip those water molecules apart, turn them into plasma, and heat them to thousands of degrees comes entirely from the onboard microwave generator. And that microwave generator requires staggering amounts of raw electrical power. To put this into concrete numbers, generating enough plasma thrust to push a medium-sized passenger plane like a Boeing 737 through the sky requires tens of megawatts of continuous electricity. That is where the entire concept hits a massive engineering wall. Where on earth do you get tens of megawatts of electrical power inside an airplane while it is mid-flight? If you try to power those microwave generators with heavy lithium battery packs, you run straight back into the exact same problem we talked about earlier. The plane becomes way too heavy to take off. If you try to run a traditional diesel or gas generator inside the fuselage to make that electricity, you are burning fossil fuels again, which completely defeats the purpose of building a water-powered engine in the first place. This is the megawatt elephant in the room that most tech explainers completely ignore. China hasn't magically eliminated the need for energy in aviation. They have simply shifted the problem from a fuel tank problem to an airborne power generation problem. For commercial passenger airlines, this engine cannot fly on standard electrical setups today. But this is precisely where the geopolitical story takes a dramatic and unexpected turn. Because while commercial airlines are stuck trying to figure out how to generate cheap megawatt-scale electricity in the air, Military strategists and defense contractors realize that there are already compact, ultra-high-density power sources capable of solving this exact problem. And that realization turns a cool university chemistry experiment into one of the most dangerous strategic developments in modern aerospace history. While Western analysts were dismissing the water plasma engine as impractical for commercial flight, strategic planners inside the Pentagon and at top American defense firms were looking at the technology through a completely different lens. They realized that military aircraft do not operate under the same budget constraints as commercial airlines. A military plane doesn't need to be profitable. It needs to perform impossible maneuvers and operate in environments where standard supply lines are cut off. Think about the massive logistical nightmare facing the US military in any modern conflict. A huge portion of military transport ships, cargo planes, and naval supply chains exist for one primary reason: to move millions of gallons of specialized jet fuel across oceans to forward operating bases. If a runway in the Pacific runs out of aviation fuel, multi-million-dollar stealth fighters become completely useless ground ornaments. Now, imagine a military aircraft that doesn't need kerosene pipelines. If a military platform uses a compact onboard energy source, such as a small modular nuclear reactor, advanced thermal electric generators, or high-density chemical power cells, it can draft local water from a river, lake, or ocean, feed it into a plasmatron engine, and generate continuous tactical thrust. Furthermore, microwave plasma engines have another massive military advantage: thermal camouflage and high-altitude performance. Traditional jet engines leave huge infrared signatures from burning carbon, making them easy targets for heat-seeking missiles. A precisely tuned plasma exhaust profile dramatically alters the aircraft's infrared footprint, and, because plasma engines don't rely on ambient oxygen from the atmosphere to sustain chemical burning, they can operate at extreme altitudes where thin air causes conventional jet engines to suffocate and flame out. This is precisely why American defense contractors like Lockheed Martin and Northrop Grumman have quietly maintained their own plasma dynamics labs for years. China's public progress at Wuhan University showed that Beijing is aggressively pushing to weaponize and operationalize advanced plasma physics ahead of the West. For commercial aviation back home in America, the pressure is mounting from a different direction. Boeing is already wrestling with severe reputation hits, supply chain delays, and intense regulatory scrutiny. Meanwhile, major U.S. air carriers are facing aggressive international carbon emission mandates that will impose massive financial penalties on conventional jet fuel within the next decade. If Chinese aerospace companies master scalable plasma propulsion and couple it with next-generation power systems, Western aviation giants could find themselves holding outdated technology. American air travel could face a scenario where foreign carriers operate on radically cheaper, fuel-free propulsion systems, while U.S. travelers remain trapped paying inflated ticket prices tied to the volatile global oil market. The technology race is no longer just about who can build a bigger plane. It is about who can control the underlying energy stack that drives high-speed motion through the air. We are standing at a historic turning point in the history of human motion. For over a century, global power, international trade, and the everyday freedom of travel have been dictated by a simple, dirty process: finding oil in the ground, refining it into kerosene, and burning it in mid-air. China's Water-Plasmatron engine is proof that this century-old rulebook is finally cracking open. By proving that ordinary water can be ionized, superheated, and accelerated to generate commercial-grade thrust, engineers have shattered the foundational myth that aviation must forever remain chained to fossil fuels. Yes, the road ahead is filled with massive engineering hurdles. Scaling a laboratory plasma chamber into an engine that can safely carry 300 passengers across the Pacific Ocean requires airborne electrical power generation at a scale humanity has never built before. It will require breakthrough compact reactors, radical battery chemistry, or hyper-efficient power grids that we are only beginning to design today. But make no mistake, the paradigm has shifted permanently. The race to dominate the skies is no longer about who controls the oil fields. It is about who masters high-density energy conversion, plasma physics, and airborne electrical systems. For the average American traveler watching ticket prices rise while legacy airlines struggle with aging infrastructure, this technology offers a glimpse of a completely different future. A future where air travel is no longer held hostage by global oil shocks, where flight is cleaner, quieter, and fundamentally detached from the finite resources beneath our feet. The flight beyond oil is no longer a wild science fiction dream. It is a real engineering program happening right now in high-security laboratories, and the country that masters it first will define the next 100 years of global transportation. Now, I want to hear from you. If a water plasma engine could eliminate jet fuel entirely, but required nuclear or ultra-high-density power systems on board the aircraft to work, would you step onto that plane for your next flight?